transformer and cell type transformer. Okay, so here core type transformer, and cell type transformer, You can divide your page into two halves and just write left hand side core type transformer and right hand side cell type transformer. Okay. Okay, right. Here, first of all, let me draw core type transformer diagram. Thereafter, we can explain. Right. Now here let me provide insulation. Let me use this red color for insulation. Yeah, let me use this red color for what? Insulation. 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 And this black color, let me show for low voltage winding. Low voltage winding. Actually, this can be called as LV3 by 2. I'll tell you why we are using LV3 by 2, all those things. We'll discuss in future. LV1, LV2, LV3 by 2. Here also same. Here I can say LV, LV. Okay. Here LV winding is there. Okay, right. Anyway. And let me show high voltage winding with blue color. High voltage winding with blue color. So this indicates high voltage winding. Here HV1, LV1, HV1, HV2, LV2, HV3, LV3 by 2, right? And as I told you, let me use black color these lines for low voltage winding. Low voltage winding. Okay. Now let me discuss. Let me discuss this one. Yeah, in core type transformer. See, in core type transformer, in shell type transformer, if you see clearly, these vertical arms can be called as limbs. Vertical arms can be called as limbs. So let me write this point here. Vertical arms can be called as limbs, or I can say legs. Horizontal arms can be called as horizontal arms. Arms like vertical portions or horizontal arms, whatever. Vertical arms can be called as limbs or legs, or equal to vertical portion can be called as, yeah, you can write anyone. Vertical portion can be called as limbs or legs. Horizontal portion can be called as okay, yoke. This vertical arm or vertical, vertical portion can be called as limbs. Horizontal portions can be called as yoke. So tell me, core type transformer, it contains two vertical arms are there, two vertical portions are there. That means what? It contains two limbs, and how many horizontal arms are there here? Two. It contains two limbs and two yokes. What about shell type also? Shell type, it contains 1, 2, 3, 3 limbs. It contains it contains 3 limbs and how many yokes? Here horizontal forces 1, 2. It contains 3 limbs and 2 yokes. Okay. And one more thing here. If you observe clearly here, these vertical portions mean cross-section area of these vertical portions or cross-section area of these limbs are equal here. Okay. So let me write here cross-sectional area of cross-sectional area of two limbs is equal this cross-section area is equal. And what about here? Cross-section area of outer limbs is 50% of cross-section area of middle limb. In this 50% is the cross-section area of outer limbs. Okay, this is more, and here 50%. Okay, so I can write here cross-sectional area of outer limbs is 50% of cross-sectional area of middle limb. And one more thing. See, if you observe clearly in a core-type transformer, where we are placing windings, on two limbs or only on one limb. Observe clearly here. We are placing windings on this limb and this limb also. Let me write here. Okay, windings are placed on two limbs. Here. And what about here? We are not placing windings on outer limbs. We are placing windings only on a middle limb only. Okay. Windings are placed on middle limb only. Next, observe clearly. If you see this core-type transformer, this transformer core, nothing but if you take a limb, okay, core is surrounded by windings, or windings are surrounded by core in this case. Obviously, transformer core is there, it is surrounded by windings. Whereas here, windings are placed on middle limb, so windings are surrounded by the transformer core. So I can write here in core-type transformer, okay, core is surrounded by windings, whereas here windings are surrounded by core. Next, observe clearly. If you see network series, if you take a circuit where current is not dividing, that circuit can be called a series circuit. If current is dividing, we will call that one as a parallel circuit. So I told you already, in magnetic quantities, flux is analogous to current in electrical quantities. So here, if you see in core-type transformer, whatever core we are seeing here, we are discussing, this core is flowing like this. It is flowing like this. Okay. Here, do we have any division of flux here? No, flux is not divided. That's why I can call this circuit, this core-type transformer as series magnetic circuit. Okay, I can call this one core-type transformer can be called as series magnetic circuit. Why? Since flux is not dividing. What about in shell-type transformer? We are placing windings on middle limb, right? So whatever flux is coming here because of current in windings, that flux pi will divide as pi by 2 and pi by 2. It will divide as pi by 2 and pi by 2. It will take path through outer limbs. So since flux is dividing, I can call this transformer as parallel magnetic circuit, parallel magnetic circuit, parallel magnetic circuit. What is the reason? Since flux is dividing, since flux is dividing. Now let me ask one more question. Since your core is surrounded by windings, that means windings are outside. Do you have any mechanical protection for windings here? Do we have any mechanical protection for windings? No. So I cannot hear no mechanical protection, no mechanical protection, no mechanical protection for windings, for windings. But what about here? Mechanical protection is there for windings. Mechanical protection is there for windings. Mechanical protection is there for windings. What is the reason? Since windings are surrounded by core, that's why mechanical protection is there for windings. Here no mechanical protection for windings. Okay. Next, if you observe clearly here, yes. Now in core type transformer, if you observe carefully here, we are placing windings horizontally. To be frank, I can explain like this. Suppose if you take a transformer core, if you take a core like this, here first they will provide some insulation. They will provide some insulation. Is it clear? Insulation. Next, we'll provide a low voltage winding. For that reason, I'll give why we have to place low voltage winding only near to transformer. Good, that anyway we'll discuss. First insulation, next low voltage winding, next insulation, next high voltage winding. Like that we are providing. Okay. This winding procedure can be called as concentric winding procedure. What is it? Concentric winding procedure. We are placing windings horizontally. So let me write here. winding procedure is concentric winding. Now what about here? See, just like a sandwich, LV, HV, LV, HV, LV, HV, like this. Okay, winding procedure is a sandwiched, or I can say interleaved type of winding, or I can say pancake winding. So let me write here. Winding procedure is okay, sandwiched. Winding procedure is sandwiched, or I can say interleaved, or I can say pancake winding. So in addition to this, let me take one more. So many difference will come here. Some more points will come. Core type and shell type. Core type, shell type. See here, next point. So as I told you, windings we are placing horizontally here. So like let me write here. Windings are placed horizontally. So if you see clearly, manufacturing point of view, if you see, since we are placing windings horizontally, it requires more amount of copper. Windings are placed horizontally, it requires more amount of copper. Here, windings are placed vertically. It requires less amount of copper. Okay, and here I'll give a small. I'll ask a simple question. So please try to answer this. How much copper is required depending on phase current. How much insulation required is depending on phase voltage. Now I am saying windings are placed horizontally, it requires more amount of copper. As I told you, it requires more amount of copper. Can you please tell me this transformer is economical for high current or low current? So don't confuse. I am saying it requires more amount of copper. More amount of copper. People generally will be having confusion. Sir, copper proportion to current, sir. Okay, so let me go for high current application. No, just think clearly. Because example, if you want me to say, suppose 100 amperes is there, like example, 100 amperes, 100 amperes. If you take core type transformer is there and the shell type transformer is there, core type and shell type is there. In core type transformer, requirement of copper for 100 amperes. Since he said more amount of copper, I am calculating copper in terms of money. Suppose if I write in terms of money, requirement of copper is more. Let me take it as 200 rupees. Whereas for shell type, it is clear that it said that it requires less amount of copper. So less amount of copper means less money than core type. So here copper requirement is example less, no, 100 rupees is less than 200 rupees. So this is the conclusion. So core type, it requires more amount of copper. Yes, more amount of money. Shell type, less amount of copper. Yes, less amount of money. Now I am asking, it is for 100 amperes. Suppose if you go for example, if you go for 500 amperes, into 5 times, I am just saying approximately, into 500 amperes. In core type, how much money it requires in core type? Into 5. If I multiply with into 5, it requires how much? 1000 rupees. Whereas here in shell type how much? Copper, how much? Rupees into 5, 500 rupees. Now observe clearly. 100 amperes, 500 amperes. Let me take this 500 amperes as large current applications. If I am going for large current applications, means example, in our example, 500 amperes, core type requires 1000 rupees, whereas it requires 500 rupees. So tell me, which one is economical for large current? Shell, copper. Clearly visible, 500 rupees only, here 1000 rupees. So definitely shell type transformer is economical for large current applications. So let me write here, shell type transformer. I can write, I will simply, already I kept heading, it is economical for large current applications. What about this one? It is economical for small current applications. Okay, this is explanation now for this statement. Okay, right, because I need some space here, I'm just going to erase this one. So similarly, I'm asked one more question. If you observe clearly, guys, here where requirement of insulation is more, see here, between LV, example I told now, this means LV winding, LV and HV insulation, core and LV insulation, LV and HV insulation, here also see, LV HV insulation, core and LV insulation. See here, number of winding sections are more, where in shell type transformer? Sections, LV 3/2, HV, LV, HV, LV, HV, LV. Like that, winding procedure is just like a sandwich. So since winding sections are more, requirement of insulation between winding sections also will be more. So obviously, you can say that in shell type transformer, it requires more amount of insulation. Reason, since winding sections are more. Whereas here it requires what? Less amount of insulation than your shell type transformer. Okay. Now tell me, same explanation once again. It requires less amount of insulation, it requires more amount of insulation. So I told you how much insulation is required based on your phase voltage. So which one is economical for large voltage, which one is economical for small voltage applications? Okay. So same thing, I'll take same example, 100 volts. Now tell me in terms of volts, right? Volts. Core is there, shell is there. So insulation I'm just calculating in terms of money. So I told you it requires less amount of insulation for 100 volts. Let us assume that it requires 100 rupees. For shell type it requires insulation how much? I told you more. More means example I'm saying. So more than 100 means let me take 200 rupees. Suppose if I go for 500 volts means large voltage applications. Core is here, shell is here. Now tell me core insulation requirement how much? 100 means it becomes 500 means into 5 times. It requires how much here? 500 rupees here. Whereas in shell type, how much insulation required in terms of money? Okay, 100 rupees, 100 volts means 200 rupees into 5. So this also into 5, let me take approximately 1000 rupees. So if I want to go for large voltage applications, in shell it requires 1000 rupees, in core it requires 500 rupees only. Therefore now tell me which is economical for large voltage applications, obviously core only, because 500 rupees here 1000 rupees. So I can write here it is economical for what? It is economical for large voltage applications. What of this one? It is economical for small voltage applications. Okay. So once again, I'm just going to erase this example. It's only for your understanding purpose. I have taken this one. So if you see conclusion, core type transformer is economical for what I said here. Economical for small current applications. Next, large load applications. Whereas shell is economical for large current applications and small voltage applications. Okay. Is it clear? Next. Now what about next point? If you observe clearly, what about leakage flux? So I think I already told you, leakage flux means what? Flux which links with either low voltage winding or high voltage winding, but not both, is called leakage flux. Now see here in shell type transformer, leakage flux will be less generally. Why? You only observe clearly. Just think clearly, just see diagram, you can understand clearly. If LV is surrounded by 2 HVs, or if HV is surrounded by 2 LVs, there will be lot of chance for leakage flux to interact with both windings. If a flux links with both windings, that becomes useful flux. That means indirectly leakage flux reduced. Since each LV is surrounded by 2 HVs, each HV is surrounded by 2 LVs, there will be lot of chances for reducing leakage flux here. So obviously, leakage flux will be less in a shell type, more in a core type transformer. So I can write that one also here. Leakage flux is more here. Leakage flux is more. What about here? Leakage flux is less here, because each LV is surrounded by 2 HVs, each HV is surrounded by 2 LVs. There will be lot of chances for interacting flux with both windings, so that leakage flux will reduce. Okay, leakage flux is less, leakage flux is more here. Is it clear? Okay. First note on this, then I'll continue. Right. Next, see guys, here one important thing you have to focus. So tell me, leakage flux is more, I'm saying in core type. Leakage flux is less, I'm saying in a shell type. Okay. Now, generally leakage flux should be less. So no, whenever leakage flux is less, then obviously useful flux will be more, power transfer capability will be more. Generally, though leakage flux is more in core type transformer, still we are using core type transformer only for electrical applications. Though leakage flux is less, we are not using shell type transformer generally for electrical applications. Why? Very simple reason. Maintenance is easy in core type transformer. Maintenance means what? Simple here. Suppose maintenance means I can say that here core is surrounded by windings. Windings are outside. Windings are outside. So if something goes wrong with windings, if any example, if any short circuit takes place between LV and HV, example, so maintenance point of view, it will be very convenient for us if transformer is core type. Suppose if it is shell type, windings are there and windings surround the core. So it's very difficult for us to maintain windings. So I can write here. I mean, so though leakage flux is more, okay, core type transformer is used for electrical applications, since maintenance is easy. Why maintenance is easy? I can say since windings are outside, so that the windings are not I can write like this: windings are not surrounded by 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 core. See, I'm using word not. Windings are not surrounded by core, so that maintenance is very easy. But here, though leakage flux is more, though leakage flux is, in shell type, in shell type, core type leakage flux is more. Shell type leakage flux, though leakage flux is less, it is not used for electrical applications. It is not used. You can write here, though leakage flux is less, generally it is not used for electrical applications. Reason, since maintenance is difficult. Why maintenance is difficult? Since windings are surrounded by transformer core. Okay, surrounded by transformer core. Note on this. Right. Now, so here, you tell me now, you make it one doubt. Sir, leakage flux you are saying more in core type. Then also you are using a core type transformer only, for electrical applications. So don't you have any methods for reducing leakage flux? Like that you may get doubt. Generally, so leakage flux generally it is more, no? But we have to maintenance point of view, we have to use a core type transformer only for electrical applications. Don't you have any chance for reducing leakage flux? Generally, yeah, indirectly, suppose winding procedure is concentric, I told here, just like a core, no, insulation, LV, insulation, HV, like that. Because of concentric winding procedure, some leakage flux will be reduced. In addition to this, one more thing is it is very, very important. Because of that, leakage flux can be reduced in core type transformer. What is that? Window factor. Okay, so let me write in core type transformer. Writing next point. In core type transformer, leakage flux can be reduced. By considering window factor. Let me WF, window factor. So what is the window factor? We'll see here. Generally window factor equals formula height of the window divided by width of the window. Height of the window divided by width of the window. So how leakage flux can be reduced in core type transformer? By considering window factor. We'll see. Very simple. First of all, let me draw a transformer core like this. Okay. If we take this one as a Just listen. You can take this portion as a window. This is what I can say height of the window. Height of the window. Height of the window can be represented with H. This can be represented with width of the window W. Width of the window W. You may get doubt. Sir, because of keeping, because of considering window factor, how can we reduce leakage flux? Very good. See, before that, I'll ask a simple question. Suppose, generally, let us assume that I just connect some source here. Okay. Now, can you please tell me here what might be the length of path of core flux? After connecting some source V1, it will take some current, I mu. After that, flux is coming. That flux will link with your primary winding. It will go like this. So no. Tell me. This is nothing but I can say core flux, right? So because of I mu, you'll get pi. Because of pi, you'll get here EMF E1. Already we discussed here EMF E1. Because of same flux, you'll be getting EMF E2 here. And according to Lenz's law, direction of phi2 will be like this. This already we discussed in last sessions. You please try to go through that. Here, what I want to ask is this black color dot lines, whatever I just shown. This is what? This is what? This black color. This is the path of your flux. Path of your core flux. Path of your core flux. Because here I want to differentiate two words: core flux and leakage flux. Okay. This dot line, whatever it is nothing but length of the mean path of core flux. Very good, guys. Next, that is length of the path of core flux. Okay. So just generally I just showed one diagram having V1, I1, I2, E2, here load voltage V2 like that. Okay, it's okay. Here, why I just drawn this figure means to show you what is the length of core flux. What is the length of the path of core flux? This is length of from here to here to here to here. This is entire length can be called as length of the path of core flux. Very good. Next, what is your doubt? Next, what is the length of leakage flux? That also you should know. Leakage flux means what? I think you might have known, already discussed it. Leakage flux means, example, you please try to refer notes. Effect of leakage flux on the operation of transformer topic. Please try to go, try to go through the topic. There I told you, example in primary side leakage flux pi L1 is there I told, pi L1. Please try to go through that. Then it will be having some clarity. So this is nothing but I can say length of the path of what? Leakage flux in primary side. Similarly here, okay, here length of the path of leakage flux secondary side. Okay, this is the length of the path of leakage flux primary side pi L1. This is length of the path of leakage flux secondary side. That means, guys, observe clearly. From here to here, this here, from here, example from here to here, 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 this portion, whatever is there, this is only I am saying length of the path of your leakage flux. Similarly, in secondary side also, this is only length of the path of your leakage flux. But whereas core flux from here to here to here to here, leakage flux is interacting with only primary winding. Then why you are taking this length and this length also? No. Core flux will link with both primary and secondary. So you can take from here to here to here to here. But leakage flux links with only primary winding or secondary winding, but not both. In primary side, pi L1 links with only primary winding, it will not come to secondary winding. So leakage flux path means this much only length you should take. And leakage flux path means this much only should take. Indirectly I can say that length of the path of leakage flux is nothing but what? Height of the window, nothing but height of the window. H I can say, height of the window H. So now please tell me, I want a reluctance for leakage flux. Reluctance for leakage flux. If you want a reluctance for leakage flux is equals to, what is the formula for reluctance for leakage flux? L by length by A mu naught mu r. Here length means don't take entire length. Here length is indirectly length, nothing but height of the window only, H I can say, H only. Now tell me, in core-type transformer, how can you reduce the leakage flux? Means, if you want to reduce leakage flux, formula leakage flux is equals to MMF by reluctance, leakage flux reluctance SL. If you want to reduce leakage flux, reluctance should be more. If you want to reduce if you want to increase the reluctance, so L should be more, nothing but height should be more. That's it. How can we reduce leakage flux in core-type transformer? Means leakage flux can be reduced by increasing reluctance for leakage flux. How can we increase reluctance for leakage flux? Means by increasing length of the path of leakage flux, nothing but height of the window. So here height of the window will be more, width of the window will be less, window factor will be more. So in core-type transformer, leakage flux can be reduced by considering window factor, taking height more, width less. So window factor will be more for core-type transformer. Is it clear? Yes or no? Next, this case we are not discussing shell type. Okay. Now you may get one doubt. Window factor is having some range. Don't go beyond that range. What is that? I can write here. So here I don't have any space. Please, under this you just write this point. What I'm just going to write here. In core-type transformer, window factor should not be more than 4. Why? Suppose some people may think, sir, I want to reduce the leakage flux a lot, sir. So SL will be more, sir. SL will, if you want to increase more, that means L should be more, sir. Height will be more, sir. If height is more, you just think, what about the useful flux? This path indirectly, this is the only path for your useful flux also. From here, it is traveling, our core flux is traveling from here to here also, no? That useful flux will reduce. So don't go beyond 4. Therefore, window factor in core-type transformer should not be more than 4. So like this, leakage flux can be reduced in a core-type transformer by considering window factor. Window factor will be more, height will be more, width will be less. This concept is not in a shell-type transformer. It should not be more than 4. Next session, we'll continue this topic only, because in addition to this, some more points are there. We'll continue in the next session with this topic only. Please note down.